Bam! In the last video, we learned pretty much the rest that we need to learn about the Perceptron. And we also learned a limitation that the Perceptron has as a linear algorithm. So in this video, we start learning how to overcome that limitation with something called logistic regression that was also mentioned in the last video. You see, just a recap, the limitation of the Perceptron is that it can only draw a straight line through data points. So a linear line straight through data points, whereas some data points might not be structured in a linear fashion. So logistic regression says we can use something called a sigmoid function, which allows the algorithm to draw a curved line through data points, which better identifies the data point classes that the data point belongs to. We'll get to see that in just a second. Now, logistic regression can be a little complex, but because we know the Perceptron, logistic regression pretty much just builds from the Perceptron. So since we know how the Perceptron works, learning logistic regression should come easy and simple. That was the whole point of learning about the Perceptron, which is the foundation of the neural network machine learning algorithm. So let's take a look at the model of logistic regression. We'll see how it builds on the Perceptron, and we'll dive into how it functions. We'll create our own logistic regression model. This time we're going to use a dataset in CSV format so you can see how it looks. We'll use supervised learning, of course, and we'll create a mini application so you can see a real life use case of a machine learning model. It'll be fun. After this video, we'll start talking about a little more of a different side of machine learning or AI. Maybe we'll talk about chatbots and also reinforcement learning. Let's dive into logistic regression first though. Really quickly, before I forget, don't forget to like the video, subscribe if you're new, comment. It helps me a lot and it's going to help with future videos as I progress series like this, especially when I get towards hacking series, defensive series, Metasploit, Wireshark, and any other kind of tool and techniques that we could think of in the cybersecurity space. Okay, let's look at logistic regression. So this is a logistic regression model, a simplified model. And as you can see from the videos on the Perceptron, it's very similar to the Perceptron with some slight changes. We see the same similarities where we have input, so we'll call that X, and the input gets a weight applied to it as it goes through the net input function, and then a bias also goes to the net input function. We'll see in a little bit that the net input function is pretty much the same as a function from the Perceptron, and that's how you know that this was kind of built on that concept. But what changes is the sigmoid function, which you see the activation function there, and the class membership probability, which is something that's new. It's not really in the Perceptron. Then you have the decision rule, the threshold function, which is very similar in the Perceptron. And then you have your output, the Y predicted. Let's take a look at this model again, but this time we're going to look at the math behind it. Okay, let's step through this with the math applied. It shouldn't be too difficult because the first half of this is pretty much the Perceptron. You already know it. Let's walk through. So you have your inputs, your X1, your X2, and your X3, and then they go to your net input function. And while they go through your net input function, they get applied to weight, W1, W2, and W3. Now you'll notice that the net input function is relatively the same as the Perceptron. You have your input times your weight, so X1 times W1, and then it gets added to something called a bias. So in this case, we have X1 times W1 plus X2 times W2 plus, Xn times Wn, however many inputs and weights there are, is however many are going to be added and multiplied together. At the end of that, you have your bias that's added to it at the very end to create an output from the net input function. Then that net input function output is sent over to something called an activation function, but more specifically in logistic regression, we call it the sigmoid function. The sigmoid function, unlike the step ladder that the Perceptron had, the sigmoid function creates a curved line. That's that logarithmic kind of mathematical function of the logistic regression. So the way that works is it creates a curved line, then sends the output off to something called the sigmoid output, where the function pretty much determines what class a data point belongs to based on probability. So if there's a high probability that a data point belongs to class 0, then it'll send that output through the threshold function, and the threshold function would make that decision that this is class 0, and that would be your output. So that's how that works. So the sigmoid function, of course, sends data over to the sigmoid output where you get a class membership probability. That probability is sent to the decision rule or the threshold function. And the threshold function, as you can see, is very similar to the Perceptron threshold function, where you have a rule. 1, if the output is greater than or equal to 0.5, and 0 if the output of the sigmoid output is less than 0.5. By the way, the 0.5 can be any combination between 0 and 1. It doesn't have to be 0.5. It's up to you to choose. 0.5 just kind of makes them equal, and it's usually a default. I mean, it could be 1 if the output of the sigmoid function is greater than or equal to 0.7, and it's 0 if it's less than 0.3, because that would equal 1. So it could be any one of those, and then you get your output. Okay, very simple, very easy. Let's create our own logistic regression model, and then let's create like this mini application so you can see how the logistic regression model works, and then we'll talk about next steps. So to create the logistic regression model that we're going to create today, instead of using a Google Colab notebook, I went ahead and just opened up a Visual Code application, which is an IDE, which stands for Integrated Development Environment. So if you don't know how to use Visual Code, it's really not too difficult. You can Google Visual Code. I'll paste a link in the description. From there, you probably just want to go to extensions, and you want to look for something called Jupyter. That's going to be what we're going to be using for this video, Jupyter Notebooks. And we're also going to use Python, so you want to make sure that you're using Python as well. All right, I'm going to create a new file. The new file must end in IPYNB for Jupyter Notebook extension. So we'll call this one, we'll say logistic regression.ipynb. There it is, Jupyter Notebook. Okay, for this, we do want to use a data set, as I mentioned, as CSV. So I took the iris data set and I imported it as CSV, and we're gonna go and train our model on this data set, the iris data set. So by the end, we should be able to classify between Setosa, Versicolor, and Virginica based on the logistic regression algorithm properties. So first, starters, of course, we want to set our imports just like in any other machine learning model. In this case, we're going to import a few things. So we want to import NumPy as NP, there we go. I don't know why, there we go. We want to import pandas as PD, there you go. We also want to import some sklearn models. So we'll say from sklearn.model selection, import train test split, which is going to help us do the train test split, simplify it. From sklearn, we want to import standard scalar. So .preprocessing, we want to import standard scalar, as this will be the scalar that we're going to use since we used this one last time. And then we want to import our linear model. So we'll say from sklearn linear model, we want to import logistic regression here. So we'll say logistic regression. I'm going to just run this just so I can load our environment, right? And so in this case, we're just going to do a Python environment. There we go. That way we have Python going. From here, we do also want to import metrics. So sklearn, we'll say metrics, import. The metric that we care about is accuracy score, but we can look at other metrics as well. So we can look at precision score, misspelled sklearn there. There we go. Precision score. We can look at recall score, and also the F1 score, which are the common ones that you look for when you're training a model. From here, we do want to import things like matplotlib and other things like that, but I'll do that later. These are the main things that we want to look at for now. Maybe when we get to looking at correlation, we'll have to go back and deploy matplotlib. But let's go ahead and move on to the next steps of our code. If you're using Google Colab really quickly, then you probably want to import drives. So it'll look something like, for Google Colab only, it'll look something like this. You'll do from google.colab import drive. And then you want to do a drive mount. So that mounts your Google Drive to the Google Colab folder for you to load the CSV from. And so this will be content/drive, and that will be the root folder for your drive. And then you will have to specify the folder you want to load where your CVE is going to be. We're not using Colab, so I can comment this out, but that's just something that I'll leave there for anyone who wants to follow along in Colab. Okay, so the first thing we need to do is load our data set. So load our data set from CSV, and we're going to use pandas to load that. So df is what we're going to use as our variable. df just stands for data frame, just a shortened version of data frame. And that's going to be pd.read CSV, and we want to read the iris dataset CSV. So we'll say iris dataset.csv, and that's going to have a delimiter, and that delimiter is going to be comma. So the reason why that delimiter is comma is because these are separated by commas here. So we want to make sure that separation exists. Okay, now we want to make sure we load our data set correctly. So we want to just view like a sample of our data set. In this case, the first 5 columns. So view sample, first five rows, not columns, first 5 rows. And to do that, we just do df-head. So just kind of viewing like a sample just to make sure that the data loaded correctly. So we want to run this. PD is not defined. Let me rerun our imports. Okay, now let's run that again. There we go. So now we see the first 5 rows of our data. We can see 5.1, 4.9, 4.7. So let's take a look. We go to the top, we can see here, right? 5.1, 4.9, 4.7, 4. So we see that the data did load correctly. And then we have our index here, 0 through 4. With Python, we start at 0 instead of 1. So you're loading the first 5. So everything looks good in this data set. The one thing we need to keep in mind is that species here are words. And logistic regression doesn't really do well with words. So we need to convert this into numbers, and we call that encoding. We call that step encoding. So we'll go through that as well. Before we get there, let's look at some more information about our data set and just make sure everything looks good. So the first thing that we want to do is see if there's any null values in our data set. If there's any empty or null values that could mess up the training of the model, so we want to get rid of those. So first I would say check for null values in our data set. And to do that, it's really easy. You just want to print simple print statement in Python, and we want to print df is null dot is null will show you the nulls, but we want to sum them. So we want to add them up just like that. So this will show us the null values, but it'll add the null values. So we should be able to see how many null values exist in our data set. So let's run that. And we see for the column sepal length 0. Actually, for all these columns, we have 0 null values, which is good. If we did have a null value, we'd have to go and fill that. So you can utilize something like df.fill NA, and that would fill all the NA values. Or you can just go to the data set and kind of fill those null values yourself. But fill NA would just kind of fill them with like, 0 or something that the machine learning algorithm can interpret. Okay, next we want to take a look at the shape of our data set, which is basically the number of rows and the number of columns. So it's really easy. So we'll say take a look at the shape of our data set, and then we can do that with df.shape, just like that. Run that, and we see there's about 5 columns and 150 rows. So just to give us some more insight, in this case, it's not really useful other than just understanding, the data set and how big the data set is. But for other data sets, it might be more useful to understand the shape of it. All right, now one thing we also want to look at is just some metrics of the data set sometimes. We don't always need to look at this, but I find it helpful just to see how the data set looks in terms of metrics like mean, standard deviation, the count of things. So to do that, what we do is we just do a df describe. So I'll say, look at other metrics in the data set. And there we go. So we have the count. So how many rows here, right? You have the mean, the standard deviation, the minimum value, and then you have some percentages, right, of those values. And then we have the max at the bottom. So just to give you more context as to, how this data set looks, I find it to be sometimes helpful. All right. Because we're using a CSV, it's important to make sure that we're checking pretty much as we can about the CSV to make sure that the data fits exactly the type of model that we want to train, but also the data fits what we're trying to accomplish as well. So the next thing we need to do is look at the D types or the object types of each of the columns in our data set. And so we'll say, look at the object types of the columns in our data set. The reason why that's important is because we want to use integers or floats when it comes to logistic regression. And if you use things like objects or strings, it might cause issues. So those are the ones that we need to encode. There are other reasons why this is important, but for this demo, this is the primary reason. So we'll say df info, and that will give us the column here, the non-null count, right? So how many non-nulls that exist. We know the shape was 150, so that's perfect. And then the type. So we have float 64, which are great. We're going to use float for these 4 here. But this last one here is an object. So that tells me that we need to actually convert this object. We need to encode it into an integer or a float. In this case, the object is species. So this is our target label as well. So we're going to be encoding our target label in just a second. All right. So before we encode our target label, I generally like to just do df. So I create like an encoded data. So we'll say encoded data equals df.copy. I create a copy of that data frame, then I save the copy in. You don't have to do this. I just find it easier to do this easier. I just find this to be easier because it lets me step through what I'm doing in real time so I can understand what I'm doing. So I'm creating a copy of the data frame that we have, and then we'll edit the copy, which is kind of realistic if you think about it. And then we'll save the copy over the original once we're done with the edits. It's kind of like how developing works in general. So in this case, we're going to say encoded data, and we want to do the species. Well, we want this one to be species encoded. So we're going to add a new column, and that's going to be equal to encoded data. We'll say species, and that's going to have a map. And what we're going to do, so what we're basically doing is taking the words and we're mapping them to numbers and species. That's pretty much it. So the first one is going to be Setosa, and we're going to convert that to the number 1. so that the algorithm knows that one is Setosa. Same thing with versicolor. We'll say versicolor, and that's going to be encoded to 2. And then the same thing with Virginica. Yep, and that's going to be encoded to 3. There we go. Now we have our encoding, and we can move on to the next steps. So now that we have our additional target label. Okay, let's look at the data set really quickly and just make sure that everything looks good. So we'll run the encode steps. Object is not subscriptable. Let's see where we went wrong. Species, forgot to do the function things here in copy. I think that was it. Yep, so the copy was a function, so we didn't specify the parentheses for copy. There we go. All right, now we can look at our data set again, and we see we have, well, actually, we're not actually looking at our data set. We're looking at encoded data because this is a copy. So let's look at that. Boom, there we go. So now we have one extra column called species encoded, and that column is float64. So this is the column that we want to use for our target label. We don't really need this column anymore because we took this column and encoded it. So for the rest of this video, we're going to use species encoded as our column instead of species. But what we want to do is, since this data frame is saved in memory, we want to get rid of that column so that the machine learning algorithm doesn't look at it. So to do that, it's relatively easy. We want to define, well, we'll do df.drop, and we're going to drop the encoded column here. So what we want to do is like that, boom, and we're going to drop the species just like that. That way in memory, the species is dropped. Actually, we're going to do encoded data.drop species. There we go. Now in memory, the species column is dropped. And if we did just as a test, we did another encoded data.info. We forgot to run this one. Let's see what we did. Specify our axis. I think that's what we got wrong. Axis 1. Let's try running that again. There we go. It wasn't really registering that correctly on an axis. So now that we dropped the species, we can run the encoded info again. Go to data.info. We see that it's, let's do this. Encoded data. Forgot to save that over encoded data. Let's do that. Encoded data. There we go. Little user errors here. So now that we see that the encoded data dropped the species and we have the species encoded, this data set is pretty much set up correctly, so we can start defining our features and our target label. So that's what we'll do in the next steps. We actually don't need this info anymore. We'll keep this info just for learning purposes. So we'll add a new cell. So now all we need to do is define our X, which is our features. So actually, before I do that, don't need the object species because we encoded it. And then here would just be, and here we're going to say display our transformed data set. There we go. Okay, now that that's out, I actually don't even know how I added these numbers here, but that's all right. Let's do our feature assignment. So the features are going to be, we're going to do encoded data dot, there, we'll do this. Now that we have our encoded data, before we continue, we're going to save our data frame into encoded data. So, or save our encoded data into our data frame. So now we can continue with df, since it'll be a lot easier to do it with encoded data. So let's run that. Boom. Now we'll say overwrite df with encoded data. Now that we know that the data set looks good. Okay. Now we can assign our X, and we'll say X equals df dot, and we want to assign X to the features. So the easiest way to do that is to drop the species encoded. So X equals df, species encoded, and that's on axis 1. Axis equals 1, and there we go, just like that. I'm gonna actually do this. There we go. Now it's going to drop the species encoded on axis 1, and then Y, which is the label, is going to be df, and that is species encoded, just like that. So now we have our features and label. So we can specify that here, define our features and label. Let's run that. Boom. Looks like everything looks good so far. All right, so now we have our data set that is transformed to work with logistic regression. We assigned our features and label. The next thing we really want to do is to look at correlation and do something called a correlation analysis. So let's look at correlation and correlation analysis. I'm not going to go too much into correlation and variance analysis in this video. I'll make a future video on that, so it'll be easier to understand. But for this video, I'll go over a brief overview of what correlation is and what we'd be looking for. So that's really easy for this. You just do df.core, because the pandas here, I forgot the library. Pandas here has this built-in library correlation. So you run that and you start seeing a correlation here. Now, it's kind of hard to understand what's going on here. I like to create like a heat map, but just know that correlation is pretty much the relationship between the different features and label in the data set. So the best way I like to explain it is, if you're selling ice cream on a hot day, the temperature of the day is directly correlated with ice cream sales. Whereas as the day gets cooler, your sales might decrease. If the day gets hotter, your sales might increase. So that's what correlation is here. In machine learning, you can have a positive correlation of maximum of 1, and then you can have a negative correlation of -1. And they, both mean two different things. But in this case, you want to have features that are correlated with a good mix. So you do want some positive correlations and also highly positive correlation, but too many positive correlations will just lead to like bias and will impact the machine learnings, how features affect each other. Whereas too little correlation would, not really benefit the machine learning model. It won't be enough of a correlation there to have any benefits between the features. So that's pretty much at an overview of how correlation works and what you're going to look for. This helps with determining if a feature is desirable or if the feature is not desirable. If the feature has a really weak correlation with a bunch of other features, it may not be desirable, or it might be, depending on what you're trying to do with your data. And at the same time, the feature's correlation is far too strong with other features, it might impact the bias of machine learning. And so that might not be desirable depending on what you're trying to do. So it's a lot of things that you should keep in mind with correlation, but the big thing is knowing what correlation is. Okay, I actually want to add a heat map for correlation. So we're going to add a few more imports here. So we're going to import matplotlib, pyplot as PLT. And I think that's all we need for this heat map here. Okay, we're going to create a correlation heat map. I like to do this because it's easier to see. And so we need to do a figure size. So plot.figure, and then we'll do fig size is, in this case, it'd be 16 and 4 because the size is, we don't want it to be too big. We want correlation matrix. So we'll do correlation matrix. So that's the matrix that we're going to see in the heat map. That's going to be equal to the features and correlation. So the correlation of the features pretty much. All right. Now we want to do the mapping for our heat map. So we'll say CMap. That's equal to SNS. So we also need to import Seaborn. So import Seaborn as SNS. All right, there we go. So that's gonna be equal to SNS diverging palette. And then we're gonna just add some numbers here for the actual graph as CMap, and that's equal to true. This is also optional, by the way. You don't need to follow this step, but this is just something I like doing when I create my machine learning model. All right, now we're gonna do the actual heat map parameters. So that's gonna be confusion matrix. We want CMap is equal to CMap, so the one we just defined. We want the Vmax equal to 0.3. Center, that's gonna be 0 center. We're gonna do square because we want the shape to be a square. There we go. That's going to be true. We want the line width. We'll say 0.5. We want annotations. So we do want to annotate. We want to format this. We're going to format this with .2f. There we go. That should be two decimal places, that 2f. That's what that format is. All right. And we want the bar, the C bar. We want that to be, and we'll say shrink, and that's going to be 0.5. There we go. All right. Now we want the title, and that's going to be feature correlation heat map, and then we want it there you go, tight layout. So we want to give that layout. Okay, now when we run this, PLT is not defined. We also need to rerun our imports. Let's just run all of it just so we can see it here. Okay, so we see a miniature heat map, which is intentional. I wanted to make it small enough where it can fit. So now we see a heat map with all of our features minus the label, right? If we want to include the label, instead of doing X core, we can just do DF core and then see the correlation even with the label. And this gives us a better understanding of how the features correlate. So in this case, we see that there's a high correlation between several features, but we also see that some features have a lower correlation. So we see the separable width has a negative correlation with the petal length. And we also see something like the petal width has a negative correlation with sepal width. So we see low correlations there, but we see things like the petal length has a high correlation with the species. We see that the sepal width has a low correlation with species. So the species is widely going to be determined by the petal length. The sepal width might not be determined by the species, but this could be valuable in looking at other metrics and other information. So in this case, we'll leave it. In a real case, if you're just looking for features that are going to be highly correlated with these species, you probably don't care too much about the sepal width. All right, let's move on because we still need to do a little bit more analysis. In this case, we're going to do a variance next. So we'll do df.var, and var stands for variance. And it shows the variance that the features have with each other and also the target label. So variance is pretty much the model sensitivity to like changing with training data. So if you have a high variance like this might be highly sensitive to changes like the petal length. So it's good to have a relatively low variance. You don't want a variance that's going to be too high unless you're looking for changes or you're looking to measure changes in those data in those features. In this case, we're not really measuring the changes in those features. We want to just make sure we have a relatively stable variance. Looks like everything looks good here. All right, now that we got the variance, we can move on. Everything looks good between correlation and variance. We don't have to remove any features. So we'll move on with all our features. Now what we want to do is define our training data and our testing data. So that's that 70-30 split that we did with the Perceptron. So to do that, we have to specify X train. We'll do X test, Y train, and we'll do Y test. And that's going to be equal to train test split, what we defined earlier. We're going to split X and Y, so our features and our label. And then we want our test size to be 0.3. So that's the 30% for a test size, which means that 0.3, there we go. Which means that the training data would be 70%. We want a random state. That can relatively be anything. We'll do 5 because random state is good because as the model trains randomly, you can keep the state of that randomization. So that state of the randomization will stay the same. So it doesn't give different results every time you want to look at what you've got. We do want to stratify the results as well. All right, now that we train our data, let's take a look. Y contains NaN, non-values. So let's take a look at what we set Y to. Y contains NaN. So let's run this again, maybe from the beginning. Let's see, still nothing. Train test, Y train, Y test, Y. Interesting. Let's take a look at what the Y has. We'll do Y dot is null. We'll run that. There we go. And we'll sum it and see if there's any null values. Okay, so it looks like there's 50 nulls and we need to see how we encoded our species. Maybe we made a typo here in the encoding of our species here. We have TOSA, there it is. So versicolor. So there was a typo here. So versicolor actually never got assigned to, it was just empty. And then Genetica looks good. All right, so we found our issue. Let's remove this. And Y should have, those NA should have been filled in Y. That's why it's good to look at your data and also to see, as you can see, it's really useful to look for where your NA values are while you're in memory for training these models. Okay, now that we fixed our typo, it looks like our train test split worked. So now we can move on to the next steps, which would be selecting our scalar and getting ready to fit the model for training or train the model with fitting. All right, so first we want to select our scalar. The scalar I'm going to use is going to be the standard scalar, the same scalar we used last time. So standard scalar, that's going to be initiated like that. And then we want to fit the data on the scalar. There we go. So as I explained in the last video, we're just kind of transforming the data to fit on that 0 and 1 scale for standard scalar. So in order to do that, we want to do X train scaled. That's going to be equal to scalar.fit transform, and that's going to be X train. So we want to transform X train on that scalar. Boom. And then the same thing with Y, or we'll say X test scaled. I'll explain that in a second. And this is going to be scalar transform, and that's X test. There you go. So fit transform for the training data. For testing, we don't need to necessarily fit it. We just transform the data. Okay, the reason why we don't do Y is because we actually already encoded Y on a scale between 1 to 3. So we actually don't need to fit those values anymore since we did it ourselves. Here, because our new feature variables are X train scaled and X test scaled, instead of just having X train and X test here, I'm going to resave these values into X train and X test. So X train will be X train scaled and X test. That will be X test scaled. There we go. It's trained. There we go. Just like that. Now we run this. We can keep our variables and they're just overwritten with the transformed data. All right. Now that we have our transformed data, we can take a look at the target label and look at the target counts. So what we'll say is, we'll say target counts. We just want to make sure that all the targets are counted evenly and the model isn't prioritizing one count over the others. So just looking more into the data. We'll say target counts, and that's going to be equal to df species encoded. And that's going to be, we're just going to look at the value counts. So that's all we want to look at. And that's a function, function. So we want to look at it like this. Now what we want to do is we want to print the target counts, and let's see what it. Okay, so we have our species, which we encoded to 1. There's 50, 2, 53, 50. So our data set is evenly balanced, which is a good thing. That's what we want, because we want to be fair with our target label and make sure that it's scaled correctly. All right, now we can define our model and we can train the data. So let's first define our model. Since everything looks good, it's going to be logistic regression, and that's going to be initiated with logistic regression. We want iterations. We don't want to iterate forever. So we'll do max iteration equal, we'll say 1000. It's a small data set. And then a random state here can be anything. I don't know. We can say 12. Sure, it can be relatively anything here. All right. Now, because the data set's pretty balanced, we don't have to like play around with too much here. Now we want to train the model. So you train on the training portion. So in order to do that, we're going to do logistic regression .fit. And now we're going to fit it into xtrain and ytrain. So the features and the label. All right. So now we're going to predict output, and we're going to save the output into y prediction. Just like in our model where the output is y pred, that's what we're going to do. So for y prediction, we want logistic regression .predict, since we want to predict data. And of course, we're going to predict our test data. We train on the training data and we predict on the testing data. So that's going to be sent to y prediction. Now there is something called probability, which is part of that sigmoid output function, as I mentioned. So we do want to include that as well. Y pred probability. That's part of that sigmoid output. And we'll say logistic regression .predict proba. Proba is predict probability, and that's x test scaled. There we go, just like that. Okay, now we could see the structure of our probability, so we can see like how logistic regression is giving a classification based on data points. So the way the sigmoid output works when it classifies data and gives a probability to that data's classification or that data's class, we could take a look at that. So we'll say look at probability classes just to see how the model is training things. We can also take a look at a visual example, which I prefer, but let's look at a non-visual example first. We'll say this is going to be, we're going to print out a message, and this is probability shape, and that shape is going to be, well, we'll do it this way. Add a format, and that shape will be y pred probability. It's going to be the probability that we defined here. All right, and then we're going to print, and we'll say sample probabilities. That's fine. We can leave it like that. All right, so to print our probabilities, we're going to say for I in range, and we want the minimum in the length of the probabilities. So the way we'll do that is we'll say min 5. So we want to only look at the 5 of them. And we want the length of probability. That's how we do it. All right, for this, we want to print if it's an instance. So we just want to print, like we'll say is instance I, because we want that one instance. And that one instance is going to be whatever the y pred probability would be. So when we run this, we should get some probabilities. There we go. So these are the probabilities that the machine learning algorithm is predicting. And it's how the sigmoid output would look once it's being sent over to that threshold function. So look at probability classes, and we'll say part of the sigmoid function, just to take a look at how that looks. Looking at this kind of thing visually, especially when you're looking at the output, is far more helpful in my opinion. But sometimes it is nice to see how the model is classifying things. All right, now we can check the actual class encoding. Well, we could check the class labels in the prediction. We know the labels are not Setosa, Virginica, and what's the other one? Versicolor. We know it's 1, 2, and 3 now, so we don't need to actually look at those encodings. We could if we want, but we can skip that. We'll now create the confusion matrix. Confusion matrix is super helpful as it shows us those metrics that we defined earlier: accuracy, recall, precision, and F1 score. It shows us a little more metrics, but those are the 4 that we imported earlier. If you don't know what a confusion matrix is, I do have a video on it, so go and click that video, and it should catch you up with understanding how the confusion matrix works and what it is. But in this case, what we want to do is we want to calculate we want to define our confusion matrix. So we'll say conf matrix, and that's going to be equal to confusion matrix. So we actually need to define our confusion matrix because it's not defined here. So what we'll do is here from sklearn. Actually, it's also part of metrics. So we can define it up here. So we'll say confusion matrix, and we'll add classification. A classification report. I think that's how it is. Oh, it doesn't like that. Oh, I added an underscore. There we go. Okay, let's go back down. Okay, now confusion matrix is looking good, and we define our confusion matrix information. So we want to focus on the test information. So that's going to be y test and the y predicted, so the output that we had. Okay, and now we want to run all so we can do our imports. All right, so what we can do here, we can print the confusion matrix. So we'll do F, and we'll say confusion matrix, and that's going to be, conf matrix. There we go. Let's rerun this. Okay, so now we have our confusion matrix where you can see here the true class is the diagonal line here, and then these other classes are either false positive, false negative, and things like that. So these are the truly predicted, and we can see that there are some ones that were incorrectly predicted, but overall most of them were correctly predicted. We could also look at the model output metrics. So we don't need to just focus on this confusion matrix to determine things. We can also look at actual metrics, which you can also derive from the confusion matrix. In order to do that, we need our metrics. So we'll say, look at output metrics. We need to define those. So accuracy score is one we need to define. We'll call this accuracy. Accuracy score, that's going to be y tests, comma, y predicted, just like in our confusion matrix, just like that. I'm actually going to copy this to make it easier. Boom. All right, so now we need precision. So precision is going to be precision score. Same thing here. For precision, we want to add an average, and that's going to be something called weighted. So we're going to use a weighted average, and that's because we're using 3 different outputs, and logistic regression is usually like a binary classification model. So it just makes it easier. We'll do recall, and this is going to be set to recall score, and that's going to be there. We also want to have a weighted average here because we're doing 3 classes instead of that binary classification. And then F1, same thing here, F1 score, and we're just going to paste that same stuff. Okay, now we got there, we can print our results. So we can print, we'll say accuracy is going to be accuracy. And then we could print, we'll say precision, and that's going to be precision. Then we can print, we'll say F1 score, that's going to be, format this, there we go, F1. And then lastly, we can do recall. We'll do recall should be 3rd. We'll do that. Print recall, and that's going to be recall, just like that. All right, let's take a look. Okay, so this is a smaller data set, which is why you're probably seeing similar results for accuracy, precision, recall, and F1 score. But on a bigger data set, especially as iterations go through, you'll see that the model outputs will be the accuracy, precision, recall, and F1 score be relatively different. You can also do things like changing the random state. I don't know, that can be 31, for example. That might also change some of these results. In this case, it didn't. So this is what we're seeing for our metrics, which is good accuracy is what we're focusing on right now, accuracy. So it's a good accuracy to have 0.91, especially for a smaller data set. All right, optionally, we could look at the classification report, which is just a collection of all of the metrics that we have. And that's pretty much just going to be, we'll do print classification, if I could spell that right, classification report, and we'll add a line break there. And then that's pretty much just going to be classification report of y test and y predicted. There you go. So once we run this, you should have a classification report of these metrics. So you see for the first label, so that first target label, we have a perfect accuracy, which is in line with our confusion matrix, 15, right? True positive. Then you have 87% for the other 2, which is in line here, right? So 13 and 2, 2 and 13, 18%. So the confusion matrix, you can get all that information from. This just makes it, looking at other metrics just breaks it down for you, so you don't have to do the math yourself. Okay, now that we got that, we can actually let's blow this up. Let's look at a confusion matrix. So this confusion matrix, we'll turn this into a heat map and blow it up. I'm not going to type it all out. I'll just kind of paste some code and then we can look at it. So just give me one moment. Okay, so we can remove this. That's just there you go. So this is the confusion matrix for our species. It's the same thing as what we looked at here. This is just putting on a heat map just to make it easier for us to visualize what's going on. That's all. All right, now that we have that, let's move on to doing our output for the logistic regression model. Now, when we're doing our output, we technically have what we need here. We don't really need to look at anything else, but what I mean by output is looking at things on like a graph so that we can see it visually. For that, I'm not going to run through the code. I am going to just paste it again, just like we did with the Perceptron, and we'll look at some things. And then from there, we'll create this realistic application so you can see how the logistic regression model works from like a application perspective. And then I'll also have this on my GitHub so that you can go and play with this yourself. So give me one moment while I paste this code. Okay, so from the output, so this is the code that I pretty much pasted for looking at the output of the logistic regression. So we can see there are 2 best fit lines that the linear logistic regression drew. Best fit linear lines, right? So we have the data points classified in red. We have the data points for green classified in green, and then we see some overlap with blue. And then the same thing with the blue, you see some overlap in green. So this is the one that got the 100% accuracy, and these are the 2 that got the 83% accuracy. So it's easier to visualize as you're looking at how the classification was done. I did mention that logistic regression does have the ability to draw curved lines as well. So although this is linear, binary, logistic regression confidence levels is something that we actually look at the probability level or the confidence level. And that can be represented in a different kind of heat map. So here you have just like a grade version of the same graph. But if you look here, you see probability for Setosa. This is the probability when it runs that sigmoid output, right? So the confidence level being the more blue. So anything on the left side of this red line here has a higher probability, and the further it goes into that blue, the higher the probability. And anything on the right side here, these are low probability. Then for the versicolor, you have a curved line here. Now this curved line, inside this curved line where the blue is, this is the highest probability. So this is where getting this classification from, just a curved line. And then lastly, you see another line drawn where the right side has the highest probability, and you see some of the green kind of slip in, which you can of course see that the red had 100% accuracy, and then the green and blue had about 83% accuracy. So that's how that works. Okay, this is how the logistic regression model is created. We just made one. Let's apply it to an application so you can see how that would look if we were to deploy this in some kind of application or something, just to help us with classifying something. In this case, we're going to classify flowers. So for this, we're going to create a file called app.py, just a standard Python file. And what we want to do is we want to, well, first start our imports. We're going to use something called Streamlit, which is a library that makes creating applications really easy. And it's helpful for understanding how machine learning can be used in applications without having to go through an entire process of, building an application per se. So we're going to import Streamlit as st, and then we're going to do from sklearn.linear model. We're going to import logistic regression. We also want to import NumPy, pandas, and standard scalar. So what I'll do here is I'll just copy these here, and we don't need train test split for this, just like that. Perfect. All right. So for this, we can first load our CSV. So load our CSV and save it to memory. There you go. Just so we don't have to load it every time it's loaded, the app will kind of store it in cache, and then it will pull the CSV from cache. So to do this, we have to specify @stcache, and that's saying that we're loading this function into cache. So this is going to be load data, and we want to return our output, our features, a label, and the data frame. So in this case, what we want to do is we're going to do data frame, right? Same thing, pd.read CSV, and we're going to read that CSV iris dataset.csv, and that's going to be, actually we don't need the separator here, it doesn't matter, it should know automatically. Now we want to encode the target label, and so just like we did with the IPYNB file, the Jupyter Notebook file, we want to encode the target label. So in order to do that, we'll say encoded data equals df.copy. We'll just kind of mimic that kind of style, and then from there we'll grab our encoded data from here, just to make things easier for us. Boom, encoded data is here. And we want to define our features. And so for our features, we're going to have, of course, X and Y. So let's take a look at our features here. And these are the same features we're going to use for our application, X and Y. And the only difference is we're not going to use DF here. And our IPYNB, we actually save DF over encoded data. In this case, we're going to keep it as encoded data. There you go. So now we have this here. We also want to drop things. So we'll say encoded data is equal to encoded data dot drop, and we're going to drop species. There we go. That way we have the same data set as we had before. All right, now that we have that, we want to return some values. We want to return our feature X, our feature Y, and we want to in turn return encoded data, and that's going to be species. And we want to return the unique values of that. There we go. All right, now we have our loaded data. Now we can initialize our variables. So X is features. So we'll just say features. Y is the label. So we'll say label. We can say target since it's target label. And then the encoded data species unique, those are target names. So instead of just the numbers, we have the actual names. I just realized because we want to use the species names, we actually don't want to drop the species names. We just want to let the algorithm kind of overlook that. So that's what we'll do. We'll do features is species encoded, and then we'll do it here just to make things easier. So we'll do drop species. So we'll drop it there. And then species encoded. Here, we'll do it this way. And then we're going to also drop species, just like that. And then for Y, we're going to drop species as well, and we'll save that on axis 1. So now we don't really want to have species in our features, and we don't want to have species in our label as well. Coded data, so we actually don't even need to drop it for Y because we're only specifying 1, whereas X we should drop it. So that's what we'll do. And then for this is going to be saved to load data because load data returns 3 variables, X, Y, and encoded data, species unique. So that's how that works. All right, now we need to specify a scalar. Let's see, define feature label and label name. And this is going to be init scalar. Initialize our scalar. We'll say scalar is equal to standard scalar, just how we did in our IPYNB file. And then we'll fit that. Feature scale equals scalar.fit, and then transform. We're going to transform the X feature. So in this case, just going to be features. All right, now we want to define our model for the app. This is like a very simplified version of what we're doing. Plus, we're not looking at our data set. We've already done that in the IPYNB file. So the model is going to be logistic regression. Max iteration is going to be the same as we did in our IPYNB file, and then a random state. We can set this as 42. Why not? We can set it as anything in this case. And then we want to fit our model, just like we did in the IPYNB file. That's going to be feature scaled and the target label. So the feature, the fitted features, and the target label is what we want to do for the training. All right, now we want to add something that this app allows us to do is we want to add classification. In this case, we'll use sliders. So we'll say classification sliders. And how this works is we're going to add feature names, and we're going to add the feature columns, and we're going to add those columns to a list. And then the sliders are going to be the values of each list. So that's how it's going to work. So we'll say feature columns to list, boom, just like that function. And then we're going to say if the length of feature names greater than or equal to 4, there you go. Then we want to add the slide bar with the column name. So add slide bar with column names. Here we go. So basically just saying there's only 4 features. So if the names, right, those names of those features are greater than or equal to 4, we want to add our slide bar. So in this case, we're going to do a title for the sidebar, and the title will say it's iris flower features. There we go, just like that. Now we want feature values, which is going to be the values as like an empty list, and we'll fill that list later. In Python, this is a list, but in other languages, this will be called an array, by the way. Okay, so for now, we want to iterate through and create our slide bar. So for that, we want to do for I name, so for the index and the name, and enumerate, and we want to enumerate our feature names. So feature names, and we want all of our feature names up to 4, because the 5th one is our target label. So we don't really care about the 5th one. All right, so for that, we want to append our value. So feature value dot append, and we're going to append, let me just enter here. We'll append the slider. So we'll do st sidebar slider, and we're going to start with the name of the slider. And this is, if you look up the Streamlit library, if you Google it, which I can share a link, this is all explained in that library as well to make it easier for you guys. Don't want to, there you go. All right, so let's enter again, just so that this is more uniform. There you go. All right, so this is going to be float value, since that was our D type, and we want the minimum value. So we're going to slide it from the minimum to the maximum of the features. So in this case, it'll be features name dot min. So the minimum value, which is where it's going to start. Whoops. There we go. And then this is going to be float, get my syntax working. There we go. Feature names, and this is also going to be the max. So names and then dot max, comma there. And then the last one's going to be the mean or the average. So I'll say features name dot mean. And that's the average. It's used interchangeably in this case. Okay, now that we have that, we can create our input data. So we'll create the input data here. So we'll say create input data for our app. Okay, so our input data will be, again, like an array of our feature values. There we go. That's what it's going to be. All right, now we want to define our input data frame. And so that's going to be pd.dataframe. And we're going to set that to feature values and then the column feature name. So the data frame is just going to be pretty much what we have. So we have feature values, and then for the, as I mentioned, for the columns, it's going to be the feature names. So we're just creating our data frame here. We also only want the first 4 columns because the 5th one is going to be our label, and the label is going to be, well, the label is used to train. We don't really want to include the label in our classification. So, and then we're going to scale our input data scaled, and that's going to be scalar transform, just like we did in our IPYNB. And I'm going to transform the data frame here, just for our model to learn. All right, now we want to make the predictions. And to do that, we can just type prediction is equal to model predict, and that's going to be input data scaled. So we predict on our scaled data. All right, now we convert our predictions back to those species names. So we'll say convert predictions to species names, and that's going to be the names that we use here, right? So we can actually just copy this because it's the same thing. We're just converting it back, and that's going to be species map, and that's equal to this. Same thing. All right, now we just want to call out our prediction. So predicted iris species, and that's going to be the species map that we created. And that's going to be the first prediction of that species map, which is supposed to be the predicted value there. All right, now that we have our prediction, we want to output that to the app. So output the prediction to the app. And then from there, we want to just set a title. Of course, that title is going to be iris prediction. There we go. Type. The next thing we want to do is we want to write something. So with Streamlit, it's st_write. And so in this case, we want to just say, we'll use bold letters. So we'll say predicted species. These stars there are to make it bold. Streamlit uses like markdown kind of syntax. And then from here, we want to italicize species just so it's easier to read. And then we'll say predicted iris species. And we'll even add some nice, cool sunglasses here. We'll say, there we go. Nice, cool sunglasses. And Streamlit supports the little emojis, so it'll add those there, which is pretty cool. All right, now we also want to show the probability. So probabilities, so that's that sigmoid output, just so you can see how the sigmoid output works. So to do that, we'll say probabilities equals model predict, and it's going to predict probabilities. To do that, we'll do input data scaled, and we're going to grab the first probability there. All right, now we want to write some probability prediction stuff. So we'll say st.write, and we're going to write, well, we're going to bold this here. We'll say prediction confidence. We want to write some more stuff here. All right, so now we want to write, if it's a setosa, we'll say setosa. And if it is setosa, we want to predict that probability. There we go. Predict that probability of, which is the first probability. So we'll say 0. And we want to format it to the second decimal place. So we'll say 2f, just like that. So now it's formatted, and then we'll throw that into italicize. There we go. We want to do the other two. So instead of rewriting this 2 more times, we're just going to copy and paste, and we'll change some values here. So setosa should be the first one. If it is a versicolor, that should be the second one. So at index 1, and then the third one is our Virginica, and that's the third one at probability 2. Okay, so now we have our prediction probabilities. So it's just, you know, the one that has the highest probability is the one that the algorithm is going to go with. That's how we're going to read that. And then optionally, just because I have images saved, I went on Google and pulled images of each of these flowers. Optionally, we want to show the image of the flowers just to make our lives easy, because we like to look at visual things as we're watching this work. So also I'll put a picture for the prediction, and this part I'll say is optional. This also helps with like if you had a real machine learning application, probably want to show a picture to help the user to understand what he or she is looking at. So we'll say if the probability is setosa, then you want the image. So we'll say for Streamlit st_image, and then we'll do images setosa.jpg. There you go. And then we're going to caption that with iris setosa, and the JPG is going to be just like that. Perfect. All right, so now we want to do this about 2 more times. So what we'll do is we'll paste and we'll paste. Now in this case, we want to do an else if. So in Python, elif, right? So now if it's predicted as, we want to add our colons here. There we go. So now if the prediction is versicolor, then we want versicolor, right? We want the versicolor JPG, and then we want iris versicolor. And then the same thing with this one. If it is Virginica, we want Virginica here, and then the iris will be Virginica. There we go. So now we have versicolor, setosa, and Virginica, depending on what it is. And this should also be an elif. All right, lastly, we want else, and this is if there's like an error or something like that. So else, we'll print out an error. That way we can, if we made a mistake, we know exactly that it's a user error instead of the model having an issue. Or if it was something that we did wrong in terms of limiting the model to the 4 features, we would have visibility into that. So we'll say, yep, not enough features. We expect at least 4 of them, because we use 4 features to predict. And those 4 features are the ones that are already in our data set. Okay, now that we have our app, we can, let's save that, and we can run our app. So if we're going to run our app, first you want to go to terminal, new terminal, right? From here, you want to create a virtual environment for Python. It's probably a lot better to do that, because Streamlit is a really wonky library. It's going to require you to create a virtual environment for Python. So to do that, you just do python-m pip. Well, we can do this. All right, so we do python-m VNV, which is for virtual environment, and then you want to specify the name of the folder where the environment is going to go into. In this case, you can just say also VNV as well, and it'll create that folder. In my case, I already have that folder, so I'm just going to call it. Once you create your environment, you want to go into that VNV scripts, and in the script is going to be something called activate. So you want to go ahead and activate that, and that'll create your virtual environment. All right, in this case, we are going to go into lecture 4. So now that we're in lecture 4, we can clear this stuff. Actually, before we go into lecture 4, we need to install some things. So let's go into our main directory here, and we need to do a python -m pip install -r and requirements.txt. So we're just installing all of the libraries in our requirements here. I need to update the requirements file. Okay, to do this, we can utilize pip tools. So we can say pip install pip tools, should install it in our virtual environment. This is just a one-time thing for me to update the requirements.txt file, but that should work. It's because we added some imports here, but we never actually included them in our requirements file. So now at this point, we can run, we'll say pip compile, we'll say upgrade requirements.txt. Okay, I updated the requirements.txt file. So now all we need to do is the same thing we did before, the python 3-m pip install -r requirements.txt. So that should install anything that we missed, and everything's updated now. So it should work on your end as well. We'll wait for this to finish and then continue. Okay, now that that's done and we ran the requirements.txt, we should have Streamlit. Well, at this point, all we need to do is go into the lecture 3. So what we'll do is lecture 4, sorry. All right, and from here, we just run Streamlit run, and we just run our app. Streamlit run app.py. Let's run that, and we should see it come up here, and let's wait a minute for it to load. Okay, so we're getting an issue here. Licenses must be integers of slices, not strings. So we need to figure out what this error is. So let's go back to our code and let's see float feature names name max. So that has to be when we're defining our sliders here. And we'll take a look. Here it is right here. So this should be, so instead of feature name, this should be features, just like that. And let's save that and let's reopen our browser and let's refresh. So let's rerun. All right, so we get our sliders and we're seeing another issue. So let's take a look and troubleshoot what that other issue would be. Fit yet now misses species. Feature name should match those that were passed during fit. So that's going to be, okay. So after a couple minutes of digging, I found that the issue is that the species map here. So this mapping is correct, but when we get back to the mapping here, this is inverted. So we're supposed to be converting predictions back to the species names, but instead we're converting species names to prediction. So this is actually, we're supposed to be using the prediction and that's supposed to be converted to the species name. So we actually had another typo here. We'll say 2, and then this will be another comma, and then this will be 3, and this will be deleted. So that's how it should look here. And this should run better if we did a Streamlit run. And let's open our here connection error. Let's reconnect that. There we go. Okay. Now that we connect, we have no error, but we are seeing a warning. SD cache is deprecated and will be removed. Please use one of Stream's new caching command, stream cache data. So we'll do cache data. We'll try that. So in order to do that, we'll have to go back to our code, and we'll see it here. There you go. We need to add that in there. All right. Now when we switch back to our window, we can rerun. And so we have our working app. So the way this works is that you have the prediction, right? This is the prediction confidence based on the sigmoid. And so you can change your sliders, and that should change the confidence levels. As you can see, versacolor, move the sepal width, which the sepal width I think was a low correlation, so it doesn't change much. It's like when you get to the higher sepal width. But you can see once you get to a higher sepal width, the setosa becomes a confidence interval, 51. And then you see the setosa have 95% and so on and so forth. So play around with these and you can get, in this case, we see the Virginica with 99% confidence levels. And so the machine learning algorithm is predicting on the back end, but it's displaying the results on the front end so we can see what the predictions are and then displaying a picture of the prediction that it's doing. This is like a cool way to show machine learning in like an app form. And just like that, you just mastered logistic regression. Thanks for sticking through. Now, it's important to note that with supervised learning and machine learning, it's one of the biggest challenges is choosing the right model for the data set that you want to make. A lot of things come into play, like desirability for performance, feature engineering, choosing the right features, model complexity, the complexity that the model has on computational time. Ideally, you want a model that's not going to take too long, that's going to classify things accurately, and that's going to have like desirable results. So things that you want to see from the model. And choosing the right model based on given data is sometimes really difficult. So for data analysts, it's probably easier to run several models against your data and compare your models, almost like putting them in a ring and letting them fight or so. And the winner of all the models is the models that you probably want to go with. So just some things to think about. Okay, for supervised learning, you've pretty much learned all that you need to know. If you want to dive further into machine learning and maybe learn the, deeper level mathematics and other things behind it, maybe I'll make some like a training series in the future. But for now, that's pretty much what you need to know about supervised learning. I am still going to continue this series with other types of AI. I think next we'll pivot into maybe AI chatbots, creating our own chatbot. Maybe we'll look at reinforcement learning. But for now, I'm going to add a few other videos on hacking, defensive techniques, and other things that people like to see before jumping back to this machine learning kind of series here. And then we'll jump into some fun stuff. Maybe we'll, see if we can train a reinforced model on something, or maybe we can see if we can detect hacking based attacks with some kind of machine learning model. It'll be fun. Again, if you like the video, subscribe, comment below. It helps me out, especially getting me out there in the algorithm as I'm trying to make some more videos, and more videos require more time, and you know how that works. Go ahead and subscribe. I'll see you guys in the next video. Pap out.